Algorithms for correlated equilibria in graphical games. Having established in Theorem 7.13 that a concise graphical game yields an equally concise representation of its CE up to pair of equivalence, we now turn our attention to algorithms for computing CE. In the spirit of our results thus far, we are interested in algorithms that can efficiently exploit the compactness of graphical games. It is well known that it is possible to compute C via linear programming in time polynomial in the standard non-compact normal form. In this approach, one variable is introduced for every possible joint action probability, P of A arrow, and the constraints enforce both the CE condition and the fact that the variables must define a probability distribution. It is not hard to verify that the constraints are all linear and there are big O of 2 to the n variables and constraints in the binary action case. By introducing any linear optimization function, one can get an algorithm based on linear programming for computing a single exact CE that runs in time polynomial in the size of the normal form representation of the game, i.e. polynomial in 2 to the n. For graphical games, this solution is clearly unsatisfying, since it may require time exponential in the size of the graphical game. What is needed is a more concise way to express the CE and distributional constraints, ideally linearly in the size of the graphical game representation. As we shall now sketch, this is indeed possible for 3 graphical games. The basic idea is to express both the CE and the distributional constraints entirely in terms of the local marginals, rather than the global probabilities of joint actions. For the case in which the game graph is a tree, it suffices to introduce linear distributional constraints over only the local marginals, along with consistency constraints on the intersections of local marginals. We thus defined the following 3 categories of local constraints, defining a linear program. Variables for every player I, and assignment A arrow to the I. There is a variable P of A arrow to the I. LP constraints. First, CE constraints for all player I and the actions A prime. The summations of P of A arrow to the I times MI of A arrow to the I, summing for all A arrow to the I such that A I to the I equals to A, which is greater than equals to the summations of P of A arrow to the I times MI of A arrow to the I under the condition that the index I is replaced by A prime, summing for all those A arrow to the I such that AI to the I equals to A. 2. Neighborhood marginal constraints for all players I. For all A arrow to the I, P of A arrow to the I, which is greater than equals to 0, and the summations of P of A arrow to the I, summing for all A arrow to the I equals to 1. 3. Intersection consistency constraints for all players I and J, and for any assignment Y arrow to the IJ to the intersection neighborhood N of I intersect N of J. P of A arrow to the IJ is defined as the summations of P of A arrow to the I such that A arrow to the I such that A arrow to the IJ equals to Y arrow to the IJ, which is equals to the summations of Pj of A arrow to the J, summing for all A arrow to the J such that A arrow to the IJ equals to 1 arrow to the IJ, which is by definition Pj of A error to the ij. Note that if D is the size of the largest neighborhood, this system involves big O of n times 2 to the d variables and big O of n times 2 to the d linear inequalities, which is linear in the representation size of the original graphical game as desired. This leads to the following algorithmic result. Theorem 7.14, for all three graphical games, Gn, any solution to the linear constraints given above is a correlated equilibrium for Gn. Thus, for instance, we may choose any linear objective function f of the set of collections of p of a error to the I and apply standard efficient linear programming algorithms in order to find a C maximizing f in time polynomial in the size of the graphical game. One natural choice for f is the social welfare, or the total expected payoff over all players. F of the set of pi of a error to the I is equals to doubling summation, with outer summation summing for all I and the inner summation summing for all a error to the I of the term pi of a error to the I times mi of a error to the I.